we'll wait a few more minutes. Hello, everybody. Hello, they're all online. We are just waiting a couple of more minutes to let some more people in so that we are not disturbed by the admit noises. And then we will start. Thank you all again to join us on this now, if my cursor managed to work, yes, seventh installment of our courses and seminars. As you can see from these slides, we have had a very healthy delivery in the last few months since April. And some were more, let's say, training courses, the first 4 of them. But now in the autumn term, we have had a number of very interesting seminars and by our invited guests. These are 2 hours conversations that we hope to continue to develop with our collaborators, but also with our audience, very importantly. And indeed, if in the audience there are colleagues that would like to deliver a seminar in the new years, please get in touch and we will try to accommodate, and we will discuss content and so on. So today, I would like to introduce the talk by Dr. Sebastian Kaminski. He's an engineer associate at Arup, and he has been here in London, and he has been working for a long time in the field of humanitarian and development constructions and reconstructions in various contexts, both, let's say, affected by natural hazards or at risk of being affected by natural hazards. So Sebastian will introduce more in detail his talk in 2 minutes, but as we are at the end of the year, I would like to just expand a little bit on our other activities behind and besides the educational offer, which, as you have seen from the previous slides, will continue from February. We already have 5 more courses programmed, and this will all be 1 or 2 day extended activities or for full training. But in the meantime, the UNESCO Chair in disaster risk reduction and resilience is also developing some actual research projects. So we are working with our colleague Xavier University in the Philippines on assessing the resilience of school and road infrastructure system in the Cagayan de Oro area. And here you can see pictures of a very interesting workshop seminar that we held at the beginning of November to receive from as a number of principals of specific school their perception of the level of hazards and risk associated with their particular school compounds, but also at the same time to understand what are their mitigation procedures and their decision-making when faced with such effects, either flooding or earthquakes. So this has been a very important piece of work in this project, which will try to turn into information that we can use in developing our artificial intelligence approach to determine the resilience of school infrastructure, for which we are also working in the Dominican Republic directly with the UNESCO Paris disaster risk reduction unit, and we are hoping to develop both Bayesian networks, agent-based modules, and cost-benefit models in order to understand, first of all, the interaction between school infrastructure and road infrastructure systems, how best we can mitigate how we can quantify the probability of damage and disruptions of education, and how we can then best identify effective recovery paths and assess their costs in order to try to optimize the choice of those recovery or indeed preparedness paths. And finally, in in Nepal, we are working with ANSET and with the universities on the structural and functional resilience of school, looking not just at the structural safety, but also looking at the functionality and sustainability of not just existing school, but also very new school compounds that have been built after the earthquake of 2015, and whether and to which extent the sustainability agenda has been considered, and how we can again help improving that viewpoint. And the issue of sustainability is indeed very important, especially with the overview of and with the concerns about climate change. So besides doing research and meeting you online, we are also been to a number of international and national events which are worth bringing to your attention. So at the beginning of November, the UNESCO celebrated an international conference for the 30th anniversary of the UNESCO Chairs programs. It was a very amazing meeting of lasting 2 days with as many as 600 attendees, one or more than one for each of the chairs that are being bestowed all over the world. As a result of these meetings, particularly, we have extended a network among European chairs, has been established, a network among UK chairs, and a network among chairs on disaster risk reductions. Now, it might be worth understanding that the UNESCO chairs are in any field of culture and science. So and in fact, the chairs in engineering and in disaster risk reduction are not so many, are just about 10. Besides that, I've been working quite a bit with the Foreign Commonwealth and Development Office of the UK government. In particular, we have contributed to a position paper on education and climate change, which should be available soon, and for which you will find a link on our webpage. This is particularly aimed at understanding the double whammy of negative actions on women's education and girls' education, coming from the effect of climate change and the effect of poor school infrastructure, and therefore how we can improve that. And finally, I had the opportunity to, let's say, herald the activity that we do within the chairs and with all of our audience and colleagues at the Institution of Civil Engineers fellow reception just last week, where again I highlighted the issue of resilience and sustainability as we cannot have a future, and we cannot have the fulfillment of the Sendai sustainability goals if we don't tackle both of these issues in the built environment more at large and in the infrastructures more specifically. And with this, as it is Christmas, I wish you, or anyway, the end of year break, I wish you all the best for the new year. And I just now let the mic to Sebastian for his very interesting presentation. Thank you.
Thank you very much, Dina. Shall I start?
Yes, please.
Right, so I'm just going to share my screen. Can everyone see that?
Yes, we can. Thank you.
Excellent, just setting up. Great, okay. Well, thank you first, everyone, for attending this talk today. I hope you find it interesting. And thank you very much, UCL, for inviting me to talk on this interesting topic. So I'm going to be focusing on appropriate structural engineering in humanitarian and development contexts. So is it possible to mute the sound when people come in, or?
Unfortunately not.
Okay, no, that's okay. No worries. So basically, globally, we desperately need more resilient homes and schools in developing countries. At the same time, we do need to maximize the use of low carbon materials, such as timber, bamboo, and soil. We have to be honest that it is more difficult to design with these. So in this talk, what I'd like to do is talk about, firstly, how we can design appropriate structure and appropriate schools and housing in these contexts while trying to maximize the use of low carbon materials. And that's not an easy balance. So a little bit about the agenda. We've got a good 2 hours here, so quite a lot to talk about, but there'll be plenty of time for questions. I'll start by setting the scene, then I'm going to talk about what is appropriate construction, and then what are the considerations to account for when considering appropriate construction in these contexts. Then I'll talk a little bit about what the barriers are, then vernacular buildings and historical community resilience. At around 2:53, there'll be a 5-minute break. So if anyone wants to go to the bathroom or grab a coffee, that's a good time. And we'll have about 10 minutes for Q&A then. And in the second part, starting around 3 or 3:10, we'll have some case studies, and we'll finish with plenty of time for questions at the end. Feel free to add questions in the chat. I won't be able to respond to them on the fly, but we can respond to them during the Q&A. This presentation is going to focus on community infrastructure, specifically housing and schools, and how we can maximize the appropriate use of low carbon materials in these contexts. These are my thoughts based on my experience, but I have to caveat that this is a very complex field. We don't have a definitive answer to all these questions and what is the most appropriate approach. So comments and disagreements are always very welcome. I think that's very healthy. Everyone has different experiences from their own different context. So let's start by setting the scene. What do we need to achieve and why? Firstly, in terms of climate change, I'm sure we all know that cement contributes towards around 8% of the global CO2 emissions. Now that's enormous, and that's something we need to do about. We need to do something about that, and urgently. At the same time, we need to consider the magnitude of inadequate construction combined with natural disasters. Around 1.6 billion people live in inadequate housing worldwide. That's a significant proportion. When we say inadequate housing, that's any sort of housing which is unsafe structurally or from other hazards or exposed to other hazards such as flooding, or it's too cramped or unhygienic. At the same time, earthquakes are actually the primary source of deaths in natural hazards, around 60,000 people per year globally on average. Some years there'll be more, some years there'll be less. So why are so many buildings in developing countries so vulnerable structurally to earthquakes? I think we can summarize this down to two real reasons. Firstly, inadequate structural design, and secondly, durability issues. When I say durability, that's the design's reached the end of its design life, or it wasn't designed properly to begin with. Geotechnical issues also play an important part, but these can be difficult and expensive to resolve structurally. The reasons behind the inadequate structural design and durability issues are primarily a lack of funds and a lack of knowledge. With both funds and knowledge, we're able to create very resilient buildings. So globally, therefore, we desperately need construction that is resilient to disasters and sustainable, low carbon, and of course, appropriate. So what is appropriate? It's one of those buzzwords that we hear a lot, but what does it actually mean? I'm not sure there's one definition for this context. This is just my definition. Appropriate construction for me is when buildings are designed taking into account all of the different considerations for that specific context. That we can call it holistic design. So what are these considerations that we need to account for when designing and selecting appropriate materials in these contexts? Let's go through them. There's quite a lot, so just bear with me. Budget. Unfortunately, that is one of the biggest constraints. It defines what we can and can't do right from the beginning. Material availability. We see in these contexts, whatever materials we have available are what we can use or can't. Local is always preferred. However, sometimes it may be more appropriate to go further abroad if for the design it's more holistically appropriate. And the material needs to be of the right quality. So a couple of examples there. We've worked on a project in Central America, and we wanted to use timber for the structure. Now, the local timber there was actually quite expensive. It wasn't properly structurally graded. It was treated with quite an old toxic chemical. So that was CCA, copper, chrome, arsenic, which is now banned for non-commercial use in, say, Europe. And it doesn't come from a reliable sustainable source. So it wasn't FSC or equivalent certified. On the other hand, we were able to source timber from the States, which was available locally, but shipped from the US, which ticked all those boxes. It was FCA certified, it's cheap, it was graded. So in that particular case, it was more appropriate to use, for us, more appropriate to select a material which came from further afield because it was more appropriate. That's just one example. There might be others, but obviously we want to go local where we can. Builder capability, something very important to really consider. Who is the builder? Are they an experienced contractor? Are they semi-skilled labor, unskilled labor, self-build? And realistically, what are their capabilities? Now, this should be defined right at the beginning of the project. Sometimes projects will just generally come up with a design, but without thinking who is the builder. It's a big difference between an experienced contractor and self-build. So if you're talking about unskilled labor, sometimes you can't use certain materials or certain technologies. And self-build is an entirely different market. It needs technologies which are really simple. So it's really important to define right at the beginning, who is that? We don't want to end up with something like this. This is a bamboo project where you can see there's a lot of splitting of the bamboo. The connection just wasn't clearly designed or built right. Designer capabilities. This is important to understand. What are the capabilities of the design team? Sometimes we might be the design team. Sometimes we might be on the client side. Sometimes we might be developing a scheme design, which then a local design team takes forward. It's important to understand what are their capabilities. Do they understand the particular material we're working with? For a recent example, we're working in a country with an NGO where they're building a community center, and we proposed reinforced block work because we felt holistically for that context it was the most appropriate. The local design team didn't have experience with reinforced block work, and that was a big issue, of course. So in that case, we actually tried to upskill them, provide some example calculations that they could then use and hopefully be able to construct that well and use it on other projects. But in some cases, we were very close to saying, well, unfortunately, what we think is the most appropriate technology, you can't use, so you need to pick a different one. But in that case, we were able to overcome that. Codes and guidance available. Are the local codes state-of-the-art, comprehensive, and easy to follow? There's very few codes in the world that actually are all three of those. The state-of-the-art codes tend to be very difficult to follow, and we have to be honest about that. And with certain materials, for example, timber, bamboo, soil, and masonry, the codes are actually very limited around the world. So many local country codes of timber, for example, are quite basic compared with the state-of-the-art. And some of the state-of-the-art codes, like the excellent ASC 41, which is one of the best seismic retrofit codes, is very challenging to use. So again, if we're wanting to do seismic retrofit in one of these contexts, just pointing towards this and expecting a local designer to be able to follow ASC 41 if they haven't much experience in that field can be quite challenging. So these can be real barriers that we have to try and overcome. Hazards. We always need to understand what hazards will the buildings be exposed to. It's really important to draw on local knowledge, but be aware of some misconceptions and also draw on broader scientific data. So for example, certain hazards may be better captured in local knowledge and certain hazards better by broader scientific data, especially where you have hazards of different return periods. So a hazard with quite a long return period may be beyond the memory of the local community, such as earthquakes. So the locals may believe that actually the area isn't very highly seismic. Broader scientific data says differently. On the other side, local knowledge can often capture things like flooding better than broader scientific data. So it's important to review both of those, try and capture that, and be aware of some misconceptions on both sides. At the same time, include fire risks, which is a real hazard, especially in things like refugee camps. That can really define your material. So hazards where events are infrequent and they may be beyond the memory of the community. One example is Haiti. Prior to the 2010 earthquake, the last large earthquake was around 170 years before, way outside of the memory of the community. And that's one of the reasons, not the only one, but one of the reasons why the buildings were very vulnerable. Structural performance requirements sought. So in humanitarian contexts, and when I say humanitarian, I'm thinking more emergencies, we can normally just achieve the best we can within those constraints. It's an emergency context. We're trying to provide shelter, schools, or warmth as quickly as we can to probably quite a large affected population. We can't achieve code compliance. Fair enough. We just want to achieve the best we can. But in longer term development projects, why shouldn't communities in developing countries have the same resilience and durability that we're working towards in developed countries? I mention this because it doesn't always happen, unfortunately. In California, for example, they routinely design, well, especially more and more now, routinely design beyond code because they know that actually it's generally better and cheaper, take into account the entire whole life of a building, to have a more resilient structure from the beginning. It's financially, it's actually a better decision to invest more money at the beginning rather than deal with the impact of a disaster. And it's the same in vulnerable communities in developing countries. Why shouldn't they have the same resilience and durability? It doesn't always happen, but in my opinion, I think it's very important that we should really strive to always have that, especially for schools. Exposure conditions for durability. This is very important to understand, and actually it's one of the areas where we see a lot of issues. So what conditions are the proposed materials being exposed to? Insects, rot, corrosion, weathering. And we should really be looking for 50-year design life. Most codes, without stating it, actually design for a 50-year design life. Reinforced concrete codes and steel codes and so forth. Even timber codes. Without stating it, they generally assume a 50-year design life. But this often isn't achieved in practice because the design doesn't cater for that, and it's mainly about exposure conditions. And we see with natural materials such as timber and bamboo that designers often underestimate the risk of rot because it's not immediate. It's not something you see on day one or after a year, but after 5 or 10 years, you can start to see that. This is an example here after the Ecuador 2016 earthquake. This is traditional housing which has suffered a lot of rot and termite attack. So again, you can see the lower part of the wall is fully exposed to driving rain. So no surprise that it's suffered a lot. And often codes in this area aren't adequate. For example, only 2 out of 11 of the main bamboo design codes that exist around the world properly tackle durability against rot. And that's a significant gap in the information. End user maintenance capabilities. So we often hear people propose that, okay, it doesn't really matter about the design life because the communities will just replace key structural elements of their buildings, of their schools, of their homes. Is that really appropriate? To have a vulnerable community have to periodically replace key structural elements. Non-structural elements is fine, but key structural elements, again, we don't do that on our houses in the UK, do we? We expect the key structural elements to last for at least 50 years. General maintenance is conducted especially to non-structural elements. It's very difficult to replace key structural elements. The end user may often forget this is important. They may not be aware of the importance of it. They may have moved out and someone else occupies the building. So, often they're not informed correctly that this maintenance is required. They may not have the resources or the technical expertise to do this. So generally, I feel it's not appropriate to require a vulnerable community to have to do this. And again, we can design buildings out of all materials, including natural materials, timber, bamboo, and soil, to have a 50-year design life with minimum maintenance. It's quite easy to do, and it has been done. So we should just go ahead and do that. Regulations and policy. Are there regulatory constraints on materials or technologies, and can these be realistically overcome? These are constraints in some countries where maybe there aren't codes in place that allow us to use certain materials. One example here is the Rohingya refugee camps, where the camp administrators didn't permit the use of some permanent materials. Sometimes we can try and engage with those regulatory organizations, and sometimes we can change their position, but it can become a constraint. Construction safety. Are there any construction-related risks associated with the proposed materials or technologies? Again, we shouldn't just design something and assume it'll be built and not care about the safety of the workers during construction. We might be picking a certain technology which requires working at height. We might be using certain treatment chemicals on the bamboo or timber which are actually quite toxic. And then we need to think, well, will the treatment workers realistically be using the right PPE? How will the chemical be disposed of? So those are real things to think about. And in many cases, from our point of view, we've actually specifically not selected some materials because we feel that actually the construction workers will be exposed to risks which are disproportionate. Requirements for extensions, adaptations, replicability. This is a tricky one. Does the design need to cater for extensions or adaptations by the end user? Is the intention that design gets replicated by the community themselves? It's actually very difficult to have a design, a school or a house, which can be simply and safely extended. Reinforced concrete can be done, but often that doesn't go quite right. And it's much more tricky to do with natural materials such as soil or timber or bamboo. At the same time, is the intention that design gets replicated by the community themselves. Full self-build construction is very difficult to influence and very difficult to create a new technology around. It takes decades for a new technology to filter down to a community so they can actually self-build it themselves. So often we see a lot of designs where people say this is going to be a self-build design, but actually doesn't go anywhere because it's so difficult to trickle down. It's important to understand the local annual climate. Again, these can affect the structural and non-structural materials. So if we have a hot climate, then the thermal mass is good, and actually heavy, large, thick walls can be good. There's other ways also to reduce the temperature in a building. So for example, light roof, large overhang, large windows, ventilations, that sort of thing. If we're in an area of high rainfall, then, and it's a school, then materials such as corrugated metal sheeting may not be appropriate because they can be extremely loud during heavy rain, to the point where actually the teaching environment doesn't work. It's far too loud for the teachers just to talk to the kids. And we have seen examples where with certain materials where the house is so warm that it's basically unlivable during the day and the community have to live outside. And that's basically a flaw in the design, but also the selection of the materials. So that can affect what material we want. Local cultural considerations, really, really important. Keeping up with the Joneses, as you might call it. So people worldwide, we all do, tend to aspire to have what they perceive to be a better, stronger, and more durable form of house construction, and one that reflects a higher level of prosperity in comparison with their neighbors. Timber, for example, is regarded as a poor man's. So bamboo is regarded as a poor man's timber, and timber is regarded as a poor man's concrete, for example. People generally want to live in a reinforced concrete or a reinforced blockwork house. That's very common. People generally don't want to live in a bamboo house or a timber house. Now, it is possible to change those sort of perceptions, and we've done it before. We did it on a project in Latin America where we developed a bamboo house. And initially the community said, actually, I don't want to live in a bamboo house. Bamboo doesn't last very long. It's not very good. I want to live in a concrete house. We showed them design. We did some workshops. By the end of that process, they'd all done a 180, and they all now preferred the bamboo house to the concrete house. So it's possible to change people's perceptions, but it's difficult. That's just one of many local cultural considerations that there might be. There may also be additional end user specific requirements, and end users will have their own requirements that we need to incorporate. They may be spatial, how they want their layout, livelihood. They may want a shop space, an open front which they can use as a shop for their livelihood. Security, they may want multiple exits, bars and windows, that sort of thing. Accessibility, all of those can affect the structural and non-structural materials of a design. Embodied carbon of materials and construction techniques. This is essential and something we should be doing routinely for every project that we're involved with now. We should be considering the whole life embodied carbon, including the design life of the entire structure. Natural materials such as timber and bamboo are not automatically a lower carbon compared with concrete and steel. They can be, they often are, but not automatically. It does depend on their design life and depends on how they're built. So sometimes, for example, for fire protection of timber and bamboo, we may have to use plasterboard, which can have sometimes quite a high embodied carbon. When you take that into account, in some cases, you may find that concrete actually performs better than bamboo or timber. It's quite rare, but it does happen. So we should be looking at the whole building embodied carbon. At the same time, we take into account the design life. If a bamboo house only lasts 10 years, but a concrete house lasts 50 years, then yes, maybe the bamboo house has a lower embodied carbon, but it only lasts 10 years, then potentially it's got 5. We're not comparing apples with apples. So we should be taking into account that design life. It's also important to understand the wider social and environmental impact of materials, how the materials being sourced, where they're being sourced from, and how is waste disposed of. This is one example here in the Rohingya refugee camps. As far as the eye can see, you cannot see any vegetation, any trees. They've all been cut down for construction and firewood. So sourcing materials from there can actually have a knock-on impact. Another example, often designers want to use naturally durable hardwood, tropical hardwood, in many developing countries. But how is that being sourced? FSC or equivalent certified tropical hardwood is actually very difficult, very expensive, and very difficult to achieve. If we're not convinced it comes from a sustainable source, should we really be using it? At the same time, how's waste being disposed of? I'm thinking in particular treatment chemicals for, say, bamboo or timber. If we're, again, keen to use a natural material, but we need to treat it with a toxic chemical, if that's likely to be disposed of close to a drinking source, that's just not appropriate. And sometimes we might say, well, we'll just tell them not to do that. But if we think that's realistically going to happen, despite the controls in place, maybe that's not the right material to select. How complex is the proposed design? Taking into account the number of stories. So if we are using some more modern, some natural materials, we have to admit that the codes are still not as advanced as, say, reinforced concrete and steel. So it may be more challenging to have a complex design or to have a large number of stories. One example, the new ISO 22156 bamboo code, which was published in 2021, which is arguably one of the most advanced bamboo codes around. We limited the number of stories to 2 intentionally because there's actually quite little data to support beyond that at the moment. In the future, we can expand that, but for the moment, we are a little bit nervous. So that's quite a lot to think about. These are in no particular order. There may be more. This is just key ones that have come to mind. But you can see there's a lot we need to consider when we're properly choosing what materials are appropriate for these contexts and therefore what technologies. So now we know that. What are the main barriers towards wide-scale appropriate construction that maximizes low carbon materials? Back to our friend budget, unfortunately, this is always a constraint. It's a bit of a misconception that bamboo and timber and soil are automatically cheaper. It's not necessarily true. If we're designing properly, sometimes they can be more expensive because more testing is required, because the codes don't have the data in place to be able to support design without testing. Certainly the same with for bamboo and soil, and with certain types of timber, that's also true. Whereas reinforced concrete generally doesn't require testing. One can just go ahead and pick up a code and use it. So unfortunately, it is a real constraint. Over time, as there's more knowledge, then that will improve, but it is a real constraint at the moment. Knowledge. This is very important. Reinforced concrete, there's so much knowledge out there. Most codes have their own concrete code or point to another concrete code that's very well established. Whereas other materials, timber, for example, the codes that are around the world, some of them are very basic. The bamboo codes, many countries don't have them, and some of the codes that do exist are quite basic. And even the most advanced codes, the Colombian and the ISO code, are comparatively basic compared with the reinforced concrete code. It's similar with soil. There's very few codes around, and also with masonry, especially simple masonry structures like reinforced masonry, confined masonry. There's comparatively few codes and guidance around. Regulations and policy. Again, if the regulations aren't in place to be able to use natural materials such as timber and bamboo, sometimes we can't use them. As I mentioned before, sometimes we can engage with authorities, and if we've got enough time, we can even start to write the codes, and that's one way of overcoming those barriers. Similar to before, community aspirations. We need to be aware that people do prefer certain materials, but it can be possible to overcome those. We shouldn't force them, but we can work with the community to describe why this material, why bamboo or timber in this particular case is now durable. How have we made it appropriate, and how have we overcome their concerns with that material? A desire to reinvent the wheel. Now, this is an important one. We often see in developing world contexts and humanitarian contexts a desire to bring in alien technologies. And on the screen now, these four aren't taken from developing world contexts. They're just general ones, but we see people trying to bring in plastic bottle housing, super adobe housing, tires, containers, all sorts of these alien, unusual materials. And people say that, oh, this could be a material that this context needs. This is their solution for housing. With these alien materials, there's often a lot of problems with them. They often don't satisfy many of the requirements that I've just talked about. So many of these are very seismically unsafe. They're not very durable. They're not an appropriate way of actually recycling waste. They can be unsafe in many different ways. Communities can't adapt them, which is very important. They can't maintain them. And communities who haven't traditionally lived in round houses generally don't want to live in round houses. They want to live in square houses. So again, these are things which are really important to consider. And in general, while we do need to do a lot more research and experimentation, the developing world is not a playground for us to experiment with, and we shouldn't be trying new alien designs on real communities. We can experiment with them offline, but when we're actually building something, we need to be confident that actually it satisfies what the community needs. Misconceptions. So like in all sectors, there are misconceptions, and I think it's important to know that because of these, we're not always building back better in these contexts. Want to highlight that beware some of the online guidance available, especially regarding seismic resistance and durability of materials such as timber, bamboo, and earth, because some of it isn't quite correct. And it's very easy to read Wikipedia, Google now, and find lots of guidance. And it's difficult to know which is what is correct. So I'd always recommend speaking to the experts and trying to, if you're unsure, try and get a wider range of different views. But there's a lot of misconceptions out there, and this isn't helped in with these natural materials, where the research is comparatively new, and people may believe they're experts after only a limited amount of work in that field. If you are working with these, I'd always recommend speaking to a structural engineer to give you advice on timber, bamboo, and earth. And if we're talking about seismic design, they should be a seismic engineer. Another example here is bamboo reinforced concrete. We actually see people trying to propose this, and we've seen people try and build with this. It's just one example. This is a technology which just doesn't really work. People are trying to remove the steel from concrete and replace it with bamboo. Now, bamboo is much weaker. It's not compatible in terms of its properties. It can rot in the concrete. And actually, if you do the analysis properly, you end up with something that has a worse embodied carbon because you need a thicker amount of concrete. Yet there still continues to be research in this field. So just beware that there are some of these misconceptions. 3 papers that I've put up here cover some of the is us trying to deal with some of these misconceptions. The first one's on bamboo reinforced concrete. The second one is durability of bamboo, and the third one, upcoming, not published yet, is the seismic performance of bamboo. Industrial pressure and corruption. So unfortunately, this can be a constraint which can stop us building with natural materials. And one example here is a project where quite a lot of bamboo houses were built. In the past, this was a very successful project. The houses were very good quality. They were very cost effective. They were very seismically resilient, especially compared with the existing housing technology within that country, which was more traditional and which was less safe and more expensive. And the bamboo project unfortunately had to stop because of some death threats from the other industry. So it does happen, unfortunately. Most new construction in developing countries is self-built. We need to be honest with that. This is real. It's very difficult to deal with. It's a real issue. It's very difficult to positively influence. Modern code compliant houses are normally beyond the technical knowledge and purchasing power of fully self-built construction. So when we're developing designs, we need to be realistic with which market are we actually targeting, and there isn't one size fits all solution. Are we trying to influence the larger self-build market, which, as I said, is difficult, but we need to try and support it, of course? Or are we doing the smaller NGO government build market, which most designs do? Most designs, when we work in these contexts, we're building a finite number of houses or schools as part of a government or NGO-led program, which is fine. But we need to be honest which market we're targeting. Again, that may affect the materials that we choose. So just briefly, were communities resilient historically? So traditional community resilience is good where disastrous events are constant and frequent and materials are familiar. And local communities generally have an excellent understanding of their own resilience and how to use familiar materials properly. Two examples here on the left-hand side, this is Nepal, a 3-story masonry and timber house that survived the earthquake in 2016. This house is 2015, sorry. This house performed quite well. It's not fully seismically resilient. The community understand its limitations. They understand how to maintain it, how to build, how to adapt with it. They understand it very well. On the right-hand side, this is a system called Bareke, which is a derivative of our Watling Daub. This is in El Salvador, and this system, which is common throughout all of Latin America, is built over hundreds of years, developed over hundreds of years through trial and error to have some seismic resistance. The communities there understand its durability, its vulnerabilities, and its performance very, very well. Another example here, this is a bamboo house in India, and inside that wall, you've actually got a bamboo frame, and they've fully protected the frame with mud. They've elevated it against flooding. They've got a good roof overhang. They know that those key structural elements in the frame are difficult to replace, and they've protected it from rot as much as they can. There's 3 external columns that are easy to replace, so they've left that outside. They understand the vulnerability of bamboo and how to use it appropriately. Another example, now in Myanmar, this is a bamboo house. The bamboo is very vulnerable to rot and insects. They've elevated it above the ground with a naturally durable hardwood. They've protected it with a good roof overhang. They really understand how to use different materials properly. And that knowledge we often forget. But where events are infrequent or change, we can start to see a change in resilience. Haiti, again, also where other effects disrupt the community. This is the Rohingya refugee camps. They were previously further inland, a little bit more protected from cyclones, and they had more vegetation around them. They're now in a more vulnerable position, having moved far closer to the coast and with very little vegetation to protect them. So they're in a much more vulnerable position. Also, where new materials, technologies are brought in, we can see a change in vulnerability. We're now in Ecuador. This is a bamboo house, it's elevated above the ground. This region is exposed both to flooding and to earthquakes. Communities are aware of both risks, but the flooding risk is more frequent, which is more important for them, more frequent event. So they've elevated it. Probably makes them a little bit more vulnerable. It's quite a light structure, so even if there is an earthquake, probably their risk to life is relatively low, but they've prioritized one risk over another. But now modern materials have been brought in. I'm not suggesting this is built by an NGO or government. My guess is this is self-build, but I don't know for sure. They've used more modern materials, but they've copied the previous design. And this house has got some good flood resistance, but it's much more vulnerable from an earthquake point of view. And potentially they're not aware of that. So they've brought in new modern materials have been brought in, potentially making them more vulnerable inadvertently. Great, so we're on time. So I thought we could have a quick 5-minute break, and then we come back at 2:55, and I'll take maybe 10 minutes of Q&A before moving on to case studies. That's okay?
That's great, Seb. And yes, please all go for a cuppa or whatever. And we will meet again in 5 minutes. And please put your comments in the chat. We already have some that we are going to look to exchange. Thank you very much.
Thanks, everyone. See you in 5 minutes. See you in 5 minutes. Hi, everyone. Yeah, is everyone back?
Hello again, everybody. Hopefully you are there. If you want to put on your video or let us know, please do so. Would you like to take some questions now, Sebastian?
Yes. So I can start with the question in the chat.
Yes, you can see that? Okay. I think
yes,
it's a very relevant one from Professor Abdul Reza Moghadam.
Yeah, excellent question. Based on your experience, do you think for appropriate structural engineering in these contexts, the roadmap should be towards developing prescriptive codes based on local practices, even for schools, or the community should be pushed to adopt more up-to-date approaches, at least for more important buildings? I think that's a really good point. I'd suggest, just again, in my opinion, that there isn't probably one answer to that, and it's not one or the other. If local practices, especially vernacular improved, can get to something approaching modern code compliance in terms of that reduction in risk and the resilience and durability, then why not? I think we don't need to choose one or the other necessarily. It's what's the best way of getting towards something that's resilient and holistically taking into account all of those considerations. In some contexts, it'll be one system, maybe a more up-to-date approach, and then sometimes it might be local practices or improved vernacular. What I've seen generally is that, say, schools, because they're larger buildings, generally the vernacular can struggle for that durability and resilience. So there may be some technologies out there, but I haven't seen many that could give us that level of confidence. So probably you'd end up having schools and other large community centers, in most cases, being built with modern materials. When I say modern, that includes natural materials, but I'm not thinking about vernacular and improved vernacular system. I'm thinking about reinforced concrete, timber, or bamboo, but with a modern approach. Housing is a bit different because the market's much larger, and that's where I think improved vernacular housing can be excellent, or even in some cases just the vernacular itself without many improvements. So that market is much larger and it's generally self-build. So I think having a bit of both there, prescriptive codes based on local practice, can work very well. But again, we should be really striving for good design life and resilience, because we can get there. Just had another question.
I don't know if
Sorry, go on.
Abdul Reza, would you like to comment further, answer to the answer? If you wish to. Otherwise, we have one more questions as well. So are there any attempts to make a scalable one solution fit all for single-story dwellings that is safe to seismic and other traditional load? What is your advice for organization trying to do so? This is from Rafik Nizarali. And again, Rafik, if later you want to comment on the answer, please unmute yourself. But Seb, to you.
So it's a good question. There have been attempts, and there continue to be attempts in the 1970s and 80s after many disasters. Many organizations, international organizations, tried developing one-size-fits-all post-disaster shelter solutions, and they generally just didn't work. It's very difficult to have a one-size-fits-all. The context varies so much. And basically the whole international post-disaster shelter community has moved away from that. And they've moved to much more flexible approaches, and often actually just providing cash or skills or very simple equipment, which feels like the right solution because it's much more adaptable. And it's up to the community to adapt that, not necessarily the international community, who don't really understand the context. We can never understand the context as much as the local community. If we're talking about longer term development contexts, again, each country, even within a country, the context can vary so much, even within the community, that I don't think there can, or we should even try having a one solution fits all proposal. Again, in my opinion, the best thing is to have a variety of different solutions, which different contexts will find appropriate in different ways. And in one country, in any country, I think there's likely to be a selection of different materials and a selection of different technologies that are used. And even if you take any developed country, say the UK, there isn't one housing technology that is used. There's multiple different ones. Same applies to developing country contexts, and we shouldn't try and force one. There's no need. It generally isn't really appropriate.
Again, if Rafik, would you like to comment on the answer? Please unmute yourself and feel free.
I think that was good, Seb. That was quite helpful. I'm happy. Thank you.
Okay, thank you, Rafik. So if there are no other questions in the chat, which seems there aren't, so I have a more general question, maybe to provide some more context here. And you have shown a very large number of different examples for different parts of the world and different contexts that have created the need for that particular development or for that particular construction. And you are referred in a number of times to projects that you have been designing for and that you have been involved in. How do yourself and Arup, to an extent, I imagine, actually get involved in such projects, which on paper would seem to be very much related to self-construction?
So within Arup, we get involved in many different ways. Sometimes we have UN organizations approaching us looking for technical support, and it may be anything from high-level technical support to detailed design and drawings. Same for NGOs, directly support us. World Bank projects, they tend to be a bit more high level. So, and sometimes even private clients working in these countries, sometimes as part of fully charitable projects, and sometimes they want to make a business out of it, but for a good cause. They want to build affordable and appropriate housing. So a whole variety of different sources have come to us. Most of these haven't been really self-build projects. They've been projects which would need to be constructed by some sort of contractor or construction manager overseeing semi-skilled labor or maybe unskilled labor, but there's someone supervising. The self-build market is incredibly tricky to enter. It's very difficult to influence, and I'm not sure
Possibly
if we can
also
easily
not
introduce technologies.
For a company like Arup.
Yes. That's also true. I think if we want to improve self-build technologies, then the best thing to do is training, is people on the ground providing training. And that happens a lot post-disaster, where many organizations go in and provide very good training to local builders for how to build back better. And it's simply, for example, reinforced concrete, how to tie rebar what's the typical detail in tying rebar that provides a better level of seismic protection.
Okay, great. Thank you very much. I don't think there are other questions at the moment, but if
Maybe,
anybody...
can I ask one more? I'm just wondering, if we are mostly focusing on how we can contribute to their learning and their better building of the structures, but in some of the cases, as you mentioned, sometimes the local knowledge is already very sufficient and high level. So how do you think like this can be transferred between locations, or bring that into the mainframe of guidelines and construction documents and so on? Like when we don't have very standard design guidelines for these kind of typologies, it becomes very difficult to convince people that this is safe and this is how it should be done. But I understand there are efforts, like in the case of Assam, there are Assam type buildings which have been there for like 200 or plus years, and they perform good in earthquakes because of the way they are constructed. And but I just wonder how these can be further enhanced and how that can be supported in the global humanitarian development aspect.
So you're thinking the vernacular systems in particular, or just general local knowledge?
I think the vernacular systems, but in general, in your experience. Like, for example, when you have a project in a very specific location, how do you extract or incorporate their knowledge into the solutions that you design?
We cannot hear you anymore, Asana.
Oh, sorry. Is that better?
Yes.
Yeah, so it's a very good question. I think one stage, right at the beginning of the design, it's really important, and in the case studies, I'll talk a little bit about it. It's very important to engage closely with the local community and the engineers and understand what their capabilities are. And all engineers and communities around the world have differing capabilities. So just to understand that, what are their limitations? What are they good at? What do they feel confident in? And draw on that experience. Reviewing the vernacular is very important, understanding its performance from a scientific point of view, that there can be some bias sometimes applied, or some misconceptions, but reviewing it scientifically, how does it actually perform? What are its weaknesses? What are its strengths? And then evaluating it and seeing if it's the right one. All that exercise can be done by local engineers or international engineers. I don't think it matters. It just needs someone to look at it with the right sort of experience. Then taking that forward and saying, okay, we want to actually promote this. It might be vernacular, it might be improved vernacular. I don't think there's one way, but guidelines are very good. Clear construction guidelines. Well, sometimes for these contexts, it's actually good to have not just a guideline, but beyond that, to have a simple, replicable design. For example, for a school, which says, okay, this is a school that uses a vernacular. It's we're confident it's resilient. It's resilient from an engineering perspective. It's resilient, and it uses vernacular systems. And these are the drawings, so people can actually build. So it can be built by organizations. In practice, though, generally, I think there's very few. We will often try and come up with these template structures, and for good reason. We say, okay, we've come up with a school, and we want to share that design and have other NGOs pick it up and then build with it. In practice, that's very rare. Most organizations, UN organizations, private organizations, NGOs, will develop their own design. They'll very rarely pick up someone else's design and say, I'm going to use that. I think it's understandable. We want to sort of develop the design ourselves. So that's just something to be aware of, that whatever effort we put in with a standardized design very rarely gets picked up and by others scaled up. Although if it's, say, a government project, the government might say, okay, actually, I like this design, and I'm going to replicate this. And that does happen.
Okay, thank you.
We've got a question from Maxat.
There is one more question by Maxat. So the question, Macaulay Beck, the question is, when contracted for the design of such local level buildings in developing countries, how do you generally solve the building services issue? Or in many areas, there is a lack of sewage system or even electricity.
That's a good question. I'll be honest.
How do you hook the building to the network if there is one or not?
That's a good question. I'll be honest, I'm not a building services engineer, and my experience in this area is is limited. There's people who have a lot more experience. I can just try and give a high level point of view. Often in these contexts, we'll try and develop an off-grid system. So off-grid latrine or something like that. And then electricity is another one. It might be an off-grid generator or solar power or something like that. But it's not something I've got a lot of experience with, and so I can't really help much on that. Shall we start with the second part then? And I see Rafik has one more question, but I wonder if we should leave that to the end.
Depending whether it's very related to the conversation that we have now, Rafik, you are welcome to mention it.
No, that can wait until the end. No, we can wait until the end. Thank you.
Okay. Please, Sebastian, proceed then.
Great, thank you. So now we're going to talk through 4 different case studies from around the world of where we have a project, we have a brief, and we have gone through the process of choosing what we felt was the most appropriate material and technology for that context. Probably worth caveating that this isn't an exact science. This was our opinion on what was the most appropriate technology, but it's quite possible that other people could come to different conclusions. Starting off in El Salvador, developing a seismically resilient and sustainable housing system. Whereas El Salvador, so it's in Central America, it's a small country, it's a very highly seismic area, very mountainous, generally quite poor as well, and has very aggressive conditions in terms of the climate's very hot and very heavy rainfall, so but quite bad for natural materials. A lot of the population still live in very vulnerable housing due to the poverty there, and even since the civil war. So there is a large housing deficit within that country. For the past 12 years, we've been working closely with a small local NGO called Redes to develop a more sustainable form of construction for housing in rural and peri-urban areas that is seismically resistant, simple to construct using semi-skilled labor, able to be constructed in poor soil conditions, durable and low maintenance, cost-effective, sustainable, uses local materials, culturally acceptable, thermally comfortable, appropriate for the community. As you can imagine, a lot of those constraints are quite obvious. It's worth stressing that in this brief, we've specifically assigned ourselves, we've said this is for housing in rural and peri-urban areas and simple to construct using semi-skilled labor. We're not trying to say this is housing that can do everything. I think that's quite unrealistic. And by trying to do that, you end up not completing the project, or ends up in the ends up being too expensive or too complex. So it's important to refine exactly who we are targeting. So in this case, it was housing for rural and peri-urban areas. Urban area housing is a different matter, it's more complex. So we've intentionally said we're not intentionally designing for that. Maybe it can be used, but we're not intentionally designing for that. At the same time, we acknowledge that by trying to develop something more sustainable, it's unlikely to be the self-build market. So we've acknowledged that it's going to be constructed using semi-skilled labor. That immediately unlocks the ability to use certain techniques which a fully self-build system may not. So we started by reviewing the existing construction systems in the country, and this is essential that one needs to do on any of these projects. We need to understand what's typically built locally. There we've got housing out of reinforced masonry, confined masonry, precast concrete, adobe. The reinforced masonry housing there, it's constructed by the majority of NGOs and the government, and actually it's very good, to be honest. It's very easy to build, hard to go wrong, durable, has good seismic resistance, and generally quite affordable as well. So we have a good technology out there. The downside is it's generally quite high carbon. As you can imagine, it uses concrete blocks and concrete infill and a lot of steel reinforcement. During this process, this is when we discovered the Bahareki system, which, as I mentioned before, it's a derivative of wattle and daub. Most countries have a derivative of wattle and daub because it's just a very clever construction system. It uses timber or bamboo, which all countries have one or the other or both. For the frame, we clad that in a matrix of timber or bamboo and finally plaster with mud. You can build it pretty much in any country, but each country has their own version. And the Bahareki system in Latin America uses a lot of bamboo. In El Salvador, it tends to use timber for the frame and bamboo for the wall matrix because there isn't a large diameter bamboo out there. And these are some examples. On the bottom, those are two photos from Ecuador after the 2016 earthquake. This housing can be multi-story, and those two houses survived. So it can be surprisingly seismically resistant. This is in Colombia, a Bahareki house which is over 100 years old, survived many earthquakes, did need some maintenance, but generally can survive well. So it can perform well when it's in good condition. So there are issues with durability, like using with most of the natural materials, durability becomes one of the big issues. This is in Ecuador, and you can see the rot and the termite attack to the wooden and bamboo frame. And that's because this lower part is particularly exposed to rain. There isn't a large overhang. That building still survived the earthquake, but it suffered quite a lot of damage. So durability is an issue with this vernacular system, but it's got a lot of potential. So then we thought, well, we've got a system which actually it's very good. It's performing very well. What can we do with it? We started to do secondary research, and we realized that actually a lot of other organizations around the world have been working on an improved vernacular wattle and daub. In bottom left, this is Costa Rica. Over 1,000 houses were built of the system in the 1980s. They're still there in excellent condition. Very successful project. Bottom right and top right, this is Colombia after the 1999 coffee growing region earthquake. They built several thousand of these houses as well. Very successful project. In the Philippines now, we've got Base Bahay, working with the Hilti Foundation, constructing 1- and 2-story housing using a similar system very, very successfully. As you can see, it looks very modern. So several thousand of this system have been built around the world. That gave us quite a lot of confidence that it's got a lot of potential. We then followed an owner-driven approach, involving the community at every stage in the process. This is very important. It gives us so much important data. It allows us to develop something which is really appropriate for that community. We involved them through workshops, interviews, focus groups. We did spatial planning workshops, try to understand what their perceptions of different materials are, what they needed from a house. Drawing all of that together, we came up with an improved Bahareki system for El Salvador. And this used a timber frame, not quite the bamboo frame we've got here, timber frame clad in a bamboo matrix with a cement mortar render. The bamboo of the timber were fully treated to protect against insect attack. All the connections are engineered. The mortar provides additional durability. And this system actually can have a design life approaching 50 years when it's properly designed. It's fully code compliant from a seismic point of view. It exceeds the requirements of the El Salvadorian code. And it's very popular with the community. This is the complete design before and after rendering. As you can see, it looks quite modern. It looks like a masonry house. The community really liked it. This is on the inside. The timber is exposed. Again, the community really liked that design, and they preferred it to masonry once you've gone through the process. We did do a lot of testing to get there, and all these other organizations that have also worked on the similar systems have done testing. That wasn't easy. We couldn't just develop it from scratch. This is just one of the tests we did. This is a full-scale shake table test of one room of the house. We tested it in Guatemala on the shake table test in the Mariana Galvez University there. And this is tested to an earthquake that's over 2 times greater than what we need to design for in El Salvador. This is an enormous earthquake. This sample had already been through around 20 cycles of earthquake, and this was the largest one. And the house was cracked, but it wasn't significantly damaged. It could be occupied immediately, and with simple repairs, it can be used. So it exceeded life safety from that requirement. So it performed very well. So that was positive. How we designed for sustainability. So we tried to minimize the embodied carbon of the house as much as possible. We used timber for the frame. We looked at using that local timber, but we just weren't convinced that was holistically appropriate to use timber, which wasn't FSC or equivalent certified and was treated with a more toxic chemical. So we have used timber that's locally available but shipped from the US because it is FSC certified. Worth mentioning that the embodied carbon of shipping actually isn't that high. The biggest impact of embodied carbon is when materials are transported by land. This probably does have a higher embodied carbon than local timber, but we felt overall this was more appropriate. The bamboo is bought locally direct from farmers, and we've treated that with boron, which is a safe to use chemical, which is still very effective against insect attack. Thermal comfort. The thermal mass of those walls actually provides some thermal benefits at night, during the day, during the hot weather, and we've incorporated other simple techniques to keep the house cool: large openings, large doors, so large windows, high level openings, and a large roof. I forgot to mention also the embodied carbon of that house is around 50% of the embodied carbon of a reinforced blockwork house. And that's because we use a lot less cement. We use around half the cement content. Even though we do have cement mortar walls, it's a lot less than blockwork. And there is wider potential for this type of system around the world. You can see in the top that distribution of bamboo around the world. Bottom are where we have highly seismic areas. A lot of those overlap. So we're working with those other organizations, and we're doing as much knowledge sharing as we can and trying to standardize the system, trying to start to break down some of those barriers so other NGOs could potentially adopt it. We've incorporated this into the ISO 22156 code, the latest bamboo structural design code, which is published in 2021. We've also written several bilingual guides on using this system. Just to emphasize that evaluations are critical at many stages of the process, and not just immediately after the building's been done, but ideally after 5, 10, 15 years, so you know how it's performed from a durability perspective. We did a lot of rigorous evaluations, and they were invaluable to find what the community thought about the design, and we've incorporated that into it. I want to stress what we tried to do on this project. We tried to select the construction material and technique most appropriate for the context. We didn't just try and push bamboo because it's known to be sustainable. So we weren't trying to push a square peg into a round hole. We were trying to maximize the use of low carbon materials, but we shouldn't start with a low carbon material and say, let's push this and make sure it's being used. What's the most appropriate for the context, and try to maximize the use of low carbon materials. Case study 2. We're now in India, in the Himalayas, developing a seismically resilient school residence building. So we're in Ladakh, in a highly seismic part of India. We're in a high altitude plateau, quite dry. We're at 3,000 meters. Working closely with the Padma Karpa School and the UK Drukpa Trust, we developed a disaster resilient form of construction for a school residence in a rural area of the Himalayas that is seismically resistant, simple to construct using semi-skilled labor, durable and low maintenance, cost effective, uses local materials, replicates the existing aesthetic. That was important for this school because it won quite a lot of awards for its aesthetic. So we had other constraints coming in there. Culturally acceptable, thermally comfortable, generally appropriate for the community, and of course, as low carbon as possible. We started by reviewing the existing materials in the area, a lot of granite available, there's a lot of mud blocks for construction, timber is also available. We also reviewed the existing construction systems, which typically, historically, where they were just mud brick buildings, and now they tend to be reinforced concrete frame with mud brick infill, non-engineered structures, just how they've now built, incorporating a modern technology with the vernacular. Unfortunately, the traditional systems, while they're durable, they're not very resilient to earthquakes. This, just an example, some of the failure mechanisms you might see. This didn't occur during an earthquake. You can just see peeling of the stone walls. So these systems can be quite fragile, even if they are durable. So putting that all together, we developed a reinforced stone masonry design for the school. This we felt was the most appropriate from a resilience point of view and a buildability point of view. It's very hard to go wrong. It's a lot of resilience for a school, which is very important. By using the local granite, it's actually, we're minimizing the use of high carbon materials. Granite's very low cost there and easy to get to, and we're not taking it from a source. We're not damaging anything. We are using a bit of concrete and cement and steel. We've tried to minimize that as much as possible. We've ended up something that's fully code compliant, very resilient, easy to build, and relatively low, not a very high cost, reasonable cost. For the thermal characteristics, we've incorporated elements such as trom walls. This is where we've got a mud brick wall, which absorbs the sun during the day and it radiates the heat into the buildings at night. And this is able to warm the buildings significantly, even when we have very cold temperatures outside, because these buildings typically are unheated. There's a non-structural risk here in terms of falling hazard from a seismic point of view. So we've restrained those mud bricks with a timber frame. For the roof, we explored different roof options. In the end, we chose to take the vernacular, which is a mud roof sitting on willow and poplars, and we have adopted that, but made it safer and made the whole system code compliant. So we adopted this in the end because it was actually quite appropriate overall. It's low carbon, easy to maintain for the community there, know how to maintain the system. It doesn't rain very heavily there, so it works quite well from that point of view. There's actually provides the durability requirements. We've engineered the system. We've got a concrete ring beam and concrete beams. So from a seismic point of view, we are code compliant and we're happy with its behavior. We've also incorporated that green mesh in the background, which prevents any mud falling through in terms of a falling hazard. And that's the finished building with a timber frame and reinforced masonry walls and mud roof. This is also an opportunity to improve health and safety on site. So we've tried to maximize the PPE that we've given to the local workers as well. Case study 3, now in Bangladesh, improving the durability and resilience to wind of shelters in the Rohingya refugee camps. So these are the camps there. These communities are extremely vulnerable to winds. So working closely with CRS, IOM, and Save the Children, we tried to maximize the durability and resilience of the emergency bamboo shelters within those limited constraints, such as, well, basically we wanted to achieve the greatest wind resistance that we could, greater durability as well. We had very limited funds, very limited materials. We're in an emergency context, so we can't achieve code. It's got to be simple to construct using semi-skilled labor, and it must not have a permanent feel, which is a political constraint. We started off working closely with our partners, providing on-site training on how to maximize the resilience of the shelters, using simple techniques such as rope bracing and roped connections. We provide additional training courses and formal guidance for the wider sector to try and support them and try and share that knowledge with them. We also conduct structural analyses of their bamboo shelters and propose simple improvements. It's surprisingly easy, often, to what looks like a complex vernacular or traditional structure, to actually engineer it, to using simple engineering techniques, determine its capacity. And that's what we try to do, and we propose simple improvements. And that's one of the improved emergency shelters that we developed closely with our partners. Case study for something much more wider: update of the international ISO 22156 bamboo structural design code. So brief history of the evolution of key bamboo structural design codes. One of the first was published in 2002 in Colombia. In 2004, an international code was published on bamboo, and in 2010, Colombia published a more detailed one. There are other available codes as well, from India, Bangladesh, Ethiopia, Peru, Mexico, and Ecuador, and others. But unfortunately, we've been seeing quite a lot of errors in design, especially regarding durability. The majority of bamboo buildings designed now don't properly consider rot, and there's a misconception that treatment solves the issue. Also, in terms of seismic and structural design, there's a misconception that bamboo is automatically seismically resilient without proper design, and we keep seeing inadequate proposals such as replacing steel reinforcement in concrete with bamboo. So working closely with INBAR, which is the International Network of Bamboo and Rattan, and the INBAR Bamboo Construction Task Force, which involves specialists on bamboo from across the world, we developed an update to 22156, published in 2021, which is a bit of a game changer in terms of bamboo. It contains derivation of design values, structural design of beams, columns, and joints, grading, for the first time detailed guidance on durability, also guidance on how to make bamboo shear walls similar to the ones that we showed you in El Salvador. Other countries are now looking to incorporate elements of this code. And to try and share this knowledge, we're also working with the Institute of Structural Engineers to publish a bilingual guide covering this in more detail. So we use this opportunity to try and basically provide a platform for which engineers around the world can start to build with bamboo appropriately and safely in various countries. So I'm just going to finish off with key messages for developing truly sustainable and resilient construction in developing countries. 1, use teams with wide-ranging skill sets. From our experience, the best projects combine multidisciplinary engineers, structural, geotechnical, seismic, mechanical, fire, electrical, public health, with architects and sociologists who understand and respect each other's views. Those projects that I mentioned, we used so many specialists from all those different fields to input, and that was really, really valuable. To use community knowledge, communities have a significant amount of relevant experience. Just make sure it's interpreted correctly and we're not taking something from one context and misinterpreting it. Beware common misconceptions in the field, especially regarding natural and sustainable materials. We see this especially regarding durability, also behavior of timber and bamboo houses in earthquakes, and sustainability of those systems. Avoid bringing in alien materials and technologies. We shouldn't view the developing world as a place for us to experiment with architecture and engineering. We should be pushing the boundaries and we should be doing a lot more research in that field, but we should only implement designs that are going to be used by communities that actually satisfy all those criteria. Those contexts are not where we can experiment. We shouldn't force the use of natural materials such as timber, soil, and bamboo where they're not appropriate or won't be accepted. We should encourage their use, and sometimes we can change people's perceptions, but we shouldn't force something where it's not appropriate. Vernacular traditional technologies tend to be excellent, often considered simply working and improving them. They're often much more appropriate and easy to be adopted. Code compliance with a 50-year design life is achievable with all materials through proper design. Just because we're using soil or bamboo doesn't mean we can't achieve 50 years. We can. It's normally less expensive and more sustainable when considering whole life costs, and it results in more resilient communities to have something that's resilient from the beginning and it lasts 50 years at least. Humanitarian developing world contexts deserve the same engineering rigor as other contexts. We shouldn't relax our engineering rigor just because of the context. Many so-called non-engineered structures can in fact be engineered. Often simple improvements, simple engineering principles can be applied to vernacular or non-engineered traditional structures that doesn't involve testing. We don't always have to just do full-scale testing. We can just apply engineering principles to understand how they work. And finally, there is no one-size-fits-all construction solution worldwide. Context always drives the solution. So in one community, a bamboo house may be more appropriate. In another one, a masonry house may be more appropriate holistically. And unfortunately, budget does also drive this. Just to finish off, what's the one thing which could have the biggest positive impact in the space? In my opinion, it's knowledge. Simple codes and guidance. We need more simple, improved codes for timber, soil, reinforced masonry, and seismic retrofit. ASD 41 is an excellent seismic retrofit code. It's just very challenging to use. If there was a simpler version that could be used by local engineers and international engineers for these sort of contexts, that would be very beneficial, in my opinion. Also, we need more codes for timber, soil, and bamboo. Thank you very much, everyone, for attending today. I hope you found it interesting. Thank you very much, UCL, again, for hosting this. And thanks very much to Arup and Arup Community Engagement for supporting all the work that myself and many others in Arup have been doing in this area. So now time for questions.
Thank you very much, Sebastian, for this very interesting overall presentation. And I think all the 4 case studies that you presented were very fascinating. I think we have a couple of questions to start with. Let me try to go back to the earliest one. There was one about siting and how do you deal with site selection issues from Emma Warren. I imagine usually there is little choice. It is just a case of including mitigation measures. How can this be included in a way that it's then scalable?
Good question. Site selection is really important, and yeah, it's a big issue because often sites are very limited. I think if we're talking about schools and larger community centres, it may be easier to say that we need a different site, and that is done sometimes. But I don't think there's one right answer here, to be honest. And it does depend on the risk of on geotechnical risk that we're talking about. Normally geotechnical, it could be flooding as well. So where we can choose a different site, we should. Sometimes mitigation measures can be quite cost effective, but there'll be a point where they're actually quite complex, and then ideally we should look for another site. And I think generally for schools, that's what's encouraged, and other community buildings. For housing, it's a bit different because communities often have far less choice. I've worked on projects where the communities didn't have an alternative. The plot of land that they had was in a vulnerable location, vulnerable to a landslide. What can you do? Well, that was their livelihood that was next to their farm, and they didn't have an alternative plot, and there wasn't an the NGO couldn't purchase an alternative plot. What do you do there? Do you build a house knowing that your house is vulnerable to landslides? I don't know what the answer is there. It's very difficult. I don't think there is one answer. I think we need to try and work through those solutions where we can, and ideally we relocate where it's appropriate, and where it doesn't affect that community's livelihood. Sometimes small mitigations can be quite cost effective. There'll be a point where the risk is too large and you have to just say, no, we can't build there. But it's a very challenging area.
Thank you very much. I don't know if Emma wants to comment back on this, or any other consideration on the issue, and also from other.
No, I mean,
please, Emma.
Seb's addressed largely what's in line with my own experience in the area. I mean, often it's an area we have to provide a considerable amount of education in terms of even considering that there may be siting issues for the community, or even for government organisations. So it's always something that I'm sort of looking to consider. But yes, it is, as Seb described, often something there are limited solutions to.
Thank you very much, Emma. Thanks. So there is
limited solution to.
Sorry, somebody's talking.
I can't hear anything.
Yes, maybe there was a bit of feedback. Sorry. So there is a question from Nibas. In many of the cases, due to practical institutional policy, engineers can practice appropriately to design building. Have you considered any stages of your studies?
So Nibas, sorry, if correct me if
I think it means, have you considered the different stages, i.e. maybe you can design, but then you will not realize it, or you need to change during the course of realization. If I'm misunderstanding, Nibas, please open your mic and rephrase.
Yeah, so yeah, Nibas, if I understand correctly, you're asking about if there are policy constraints that means that we can't build in a certain way or use certain materials. I think it's a good point, and ideally that we try and find that out as early as possible, right at the beginning of the process, when we're doing the community research, when we're working out when we're learning what materials and techniques are locally available. Also at that stage, we understand, we look to see what other constraints there may be, such as policy, and can this be overcome? Is it just an issue of talking to the local authorities, or is it something that we can't change? So it should be done right at the beginning of the process. Sometimes we might only find, even if we try at the beginning, we may only find out about it later, and then unfortunately the design may need to change, or again, if you go back to the authorities. In some of these solutions, we have effectively engaged with local authorities to and permitted alternative construction to be used. That involves typically more time, good relationship with the authorities, and lots of evidence. But for example, the bamboo housing system, which has been developed, Base Bahay, who are working in the Philippines, they are working very closely with the government. They've got a very good relationship, and the government has permitted that system to be used. So it can be done. It just takes more time, and you need a lot of evidence to support your case, to show that it's structurally sound.
And again, Nibas, if you want to comment on the answer. Any other remark on the topic from anybody else? It seems not. So let's move to the next questions. Is the housing solution for these areas is for each area, I think it's a particular solution. And that solution goes by knowing the people after deep community work with them, as nothing can be imposed from outside their community. I don't know if this is from Luis Moran, and I don't know if you were referring to one of the particular case studies or whether this is a more generic comment. Luis? Otherwise, Sebastian, I leave it to you to comment on it, on the topic.
Yeah, no, I fully agree with Louisa's statement. Housing in particular is very bespoke, and we can only work. We have to work with the local community, find out what they need, what their needs and desires, what their perceptions are, what is appropriate. So, what the community, their opinion is invaluable, and it's part of the appropriateness. So that's really, really important.
Again, Luis, I don't know if you want to comment on this. It seems not. I have a couple of questions. The first one is, again, a more general context one, and relates to this last slide that you have here. You are saying affordable post-disaster construction, and I would like to, and I see that they are all basically large NGOs or even global institution projects, which have produced these publications. And so the affordable is affordable for whom? It's affordable for the local government, that is, or the national government, that is, or some international funder, or is it affordable for the local community and therefore for the people that are going to live in them?
I think that's a really good question. So when I say affordable, I'm thinking it's a very subjective word. I think I'm not saying it's the best word here. I'm thinking more affordable or low cost. I prefer the word affordable, but typically for NGOs and government institutions, in housing, it's a bit different. So it's very difficult to, in all countries, there's a threshold of cost, which may be roughly between $5,000 to $10,000 in different countries for a 40-meter squared house. And below that, it's probably not possible to get a house which is code compliant and is resilient. So, and that sort of cost is probably beyond, well, it's beyond the purchasing power of many, over 1 billion people around the world. So code compliant housing is just unaffordable for many people. I don't know what the answer to that is. I think that's in the self-build sector, which is very complex. I'm thinking here more for the government and NGO build sector, where, in my opinion, I think we should be building generally low cost but resilient and code compliant housing in schools, and I think we can do it. In the self-build sector, it's much more tricky, and I don't know what the right solution is there.
Thank you, Seben. So what then? I have a follow-up question. So if you think about this, do you think that you said that basically between $5,000 and $10,000 for 40 square meters, which is not a villa, of course, it's just basically 40 square meters is one bedroom and one living room with services. Do you think that if that is, if the design just scaled up to large, let's say, production of these houses or large construction programs, then it becomes more efficient and scalable, and therefore the resilience can be enhanced.
I think that sort of cost in my head was assuming it's been scaled. So as a one-off, you could be easily double that. But
Okay.
when you're scaling these, just from my experience, I think that's the sort of cost for a scaled, code compliant, but low cost house. So the bare basics, but it's code compliant in many countries. That's the sort of minimum threshold. Below that, you just start eating into the resilience. But that's assuming it's constructed at scale. So you've already got economies of scale in there.
So, and when you're saying scaling here, we are talking hundreds, we are talking thousands, we are talking tens of thousands.
Potentially, I think you do get decreasing economies of scale beyond a certain point, because a lot of this is, even if you set up a factory to sort of support this, there is advantage in prefabrication, but with some technologies, it's actually easier to build on site. So, for example, reinforced block work, it's difficult to prefab that, and it's easy to build on site. So, scaling probably doesn't give you a big economy of scale. And with some bamboo housing systems, they try and prefab the systems in the house, whether you're building several hundred and you're prefabbing them or several thousand. You probably don't get an enormous economy of scale, is my guess. You'll get some savings, but there'll be a limit to it.
Okay, thank you very much for your answer. And well, the conversation could go
Maybe
on.
Can I add one comment?
Sure, right.
So maybe I will be repeating some of the discussions before, but I will be sharing some experience from Nepal's reconstruction after the 2015 earthquake. I think the reconstruction activity is now almost over, 90% or more constructed, fully constructed. So when looking at in general, looking at the reconstructed houses, private houses, the community houses, it appears that the houses do not integrate very well to the socio-cultural aspects of the communities. It looks like government gave some very standard seismically resistant, but not integrated, socially integrated houses. So my observation is that, for example, people were constructing houses traditionally, historically, since long time, and they were affording those houses. For example, there are 2-3-storied masonry houses with some timber elements in most of the hilly regions in Nepal. So what if we applied some seismic resistance, let's say seismic enhancement elements to those houses, rather than giving them different modern options like foreign materials and so on? Well, if we had consulted properly to the communities about improving their existing construction technology, and that would have been more sustainable, more affordable, let's say, and socially, culturally blended to their lifestyles in the remote areas. So how do you see this? If you want to add, or if you want to comment on my view, please.
I think that's a really good point, and so I'm just sharing on screen one of the housing systems that we saw in Nepal after the earthquake as well, and I'd agree that actually working with vernacular systems and sometimes simple improvements can have a big impact. And you've already got something which is familiar, the communities understand it, and it's got some resilience. It's appropriate already because it's been there. It's generally developed through trial and error to be appropriate. So I fully agree.
I think although we were not successful in such holistic resilience in Nepal, I think we could learn lesson from this and then apply to similar context in other countries or even in future earthquakes in Nepal.
No, I think that's true. One thing I would add there is that, yeah, we should definitely try and improve vernacular. Sometimes it can be quite tricky. So I'm not saying we shouldn't do that. I'm just pointing out some of the issues that can come up. And one issue that we saw, we did a little bit of work in Nepal, was the timber type. So a lot of the traditional timber was, I forget the exact species, but I think they called it ironwood informally, and it's a naturally durable hardwood, and it's got quite a lot of durability to rot and insect attack. And there are very few timbers around the world that actually have durability to rot and to both rot and insect attack. But I believe this one did. It was a very naturally durable timber. Problem is now it's very expensive, and it's very difficult to source. And we've seen this in other countries, in El Salvador as well. Traditionally, they used naturally durable hardwood for their frames. Now that's no longer available. So if we're trying to replace the timber, what do we use? We need to use something that's sustainable. We can't just chop down our hardwood forests. And the treated timbers generally don't have the same performance. Even some of the best safe treatments out there, such as copperazole, won't give you the same performance as a naturally durable tropical hardwood. So that's just a real constraint. I don't know. It means that we may need to adapt the design, but we've seen issues where people just try and remove a naturally durable timber and replace it with a treated timber, and it doesn't work. So just something to, I guess, we need to bear in mind. But I agree with what you're saying. That
what I was referring to was not only about timber, but also about the stone available locally. That is more sustainable way, because from the rubble of the damaged houses, we had so much of stone, but they were not used. They were all wasted, replaced by bricks. So we could explore further on this. Thank you.
I think this conversation opens up another very interesting conversation about the exploitation and market of hardwood globally across the world, and why is it not in existence, or why it's so difficult to source anymore, and where it has been used instead, or where it is being used instead. So, but that would be another lectures possibly. There is one more question about bamboo and whether it's again from Nibas is asking whether in low seismic areas it is worth optimistic and economic to design seismic resilience bamboo or similar houses with a lifespan of no more than 10 years. Does it make sense in areas that don't have seismicity? Can you choose materials that maybe are less resilient? I think that's the gist of the question. But to me, they still need to be sustainable, because the fact that they will not receive an earthquake doesn't mean that they should deteriorate. But please, Seb.
Yeah, no, I'd agree with that. I think if it's low seismicity, then we should the design constraints, structural design constraints become less. But in my opinion, that doesn't change the durability that we should aim for, because that durability, yes, you're less worried about your house collapsing because your earthquake risk is low, but we don't want to have a house where we've helped the community develop a house and after 10 years, well, that house is suffering, because durability is such a big issue that houses may need replacing after 10, 15 years. We have seen this. So rot and insect damage is often so significant that your structure has basically failed, or it's in the process of failing. So I think regardless of the earthquake risk, we should be aiming for 50-year design life where we can.
Thank you very much, Seb. And we didn't mention the effect of ants and mites on natural timber or mud structures, which are also environmental issues, even where there is no, in fact, where there is not so much humidity and moist. The one last question that I wanted to ask you is about the bamboo structures, because in my travelings in Peru, I've noted, especially in the south of Lima, that in the more dry, arid part of the country, they do build a lot of brickwork or blockwork walls, which are then topped by floor structures which are made with half bamboo filled in with poor concrete, basically, and virtually no reinforcement. And this is a very common practice in many urban areas, as well as let's say rural area, less. They are clearly a sort of transitional form from a more traditional to a more modern, but they are certainly a typology that is quite spread. You were mentioning earlier that some of the work and tests that you have done show that bamboo and concrete are not a good mix. So I would like to hear more about that.
So I can't quite picture the system you're talking. Is it where you have bamboo or timber bracing and you've got masonry infill?
Basically, the bamboo is used as formwork for the concrete slab, but the slab usually are quite thin. So you will have half bamboo sitting one next to the other, and then concrete poured on top of them.
So this is for the slab. This is the slab construction technique. Okay. Yeah.
And then it's somehow connected to the wall structure, but the wall structure is not necessarily made of bamboo. It's made of blockwork or brickwork.
So I think I have seen that. So obviously that gives you initially can be a stiff diaphragm, probably with very little capacity once it starts to crack. So I've seen that before. I think it can be an option. It gives you quite a bit of good dynamic performance of the floors, so that it probably behaves well, good acoustic performance, which is one of the downsides of using natural materials in your floors. You can get quite a lot of vibration and poor acoustics, so that definitely helps. The downside is the mass that you've added, possibly quite a lot. I think it depends on your lateral load resisting system. If you're confident it can take it, then a thin concrete topping for vibration and acoustic purposes probably isn't the end of the world. If you're confident that your structural system, your bracing system, or your shear wall system can deal with it.
Well,
I think
it's not a design structure. It's just very common and very prevalent. But I think that again goes back to the area of the self-build. Okay, there are no more questions, I think, and many are thanking you already for the great presentation and the conversation that we had. I think I can only join in applauding this very interesting exchange, and to thank all the audience for their interesting comments, and to future meetings in the new years, and merry break and best wishes for the season to everybody.
Thank you everyone for joining. I hope you enjoyed it, and thank you UCL for hosting.